equilateral, to be exact, more exact. Okay, so basically you can represent the body in terms of 3 electrodes, one on your left hand, and this is the left voltage, that's why we say LV, the right voltage, and the voltage at the left foot, okay? And this is how we put our electrodes on top of the body in order for us to measure electrical potentials, okay? Now, in the analogy that we did before, exactly like we drew up before this egg, as I say, to the isopotential lines, remember, and we took 2 points on it. Remember that?
Yeah.
Exactly the same way. Exactly the same way we can measure between this electrode and between this and that electrode. And between okay, this is the arrangement of our voltmeters. And we call these voltmeters Latin 1, Latin 2, and Latin 3. You're sick and tired of Latin, I know, but are we clear on that? Okay, let me go back to my slides for a minute. You recall this slide? This shows you how we put how we measure. It is exactly what we said here before, but now you see it on a real torso. The basic thing you have to remember is that whether we measure at the thigh or farther down at the foot, or at the shoulder or farther down at the hand, the difference is not going to be big, because we are really looking at what happens inside the heart. Pretty much the body can be approximated by a bag, like I did before in the drawings that I drew for you. If that approximation was not holding, then everything we're talking about was not going to be so. But that approximation holds. Okay? Think of yourselves as a bag of salt water. We said that before, right? So, now let's go back to the drawing board for a minute. If in the middle of this, triangle we consider that we have our heart pumping. Okay? Then this we can assume that it is placed exactly centrally. All these are assumptions, but these are assumptions that have been proven experimentally to indeed hold. So you don't have to worry at this point about them. Just consider that what we are measuring really can be measured. So, if this is so, any moment, any instant, this heart is going to have to be represented, let's say, by a dipole. Okay? This is the sum total of the small dipoles of every cell in the heart, right? Right? Okay. So let's say, for the sake of the argument, that at one particular instant, we are drawing here an arrow to represent this dipole. Okay? Then, what are we going to measure in our first voltmeter? Voltmeter Latin number 1. We are going to measure, okay, this dipole, but only as far as it projects on this axis between LR and LV, that is between the right hand and the left hand. What do I mean project? You know what a projection is. Is, let's say, the shadow. If we have a line, and we have an arrow like this, a vector, then what is the projection? The projection is the impression of that vector on the line when we bring two perpendicular lines down. This is a perpendicular, this is a right 90-degree angle. Okay? This is therefore the vector. And this is the projection. Okay? We understand what a projection is? Hello? You?
Yeah.
So we understand now what a projection is, correct? Since we understand what a projection is, and we said that in order to project, we need two perpendicular lines. Coming back here, if we put our electrodes in the right hand and the left hand, what we are going to measure is the projection of the vector inside the heart onto the straight line that connects the 2 points together, onto this side of our triangle. Okay? Is that understood?
Yeah.
Good. Now, let's go to the other electrode. Αυτό που έβγαζε από κάτω ήταν. Κλικ, κλικ, πέρα. Θόρυβος που κοβόταν. Εκεί κάποιο κινητό ήταν. Hello? Now, let's take the other pair of electrodes between the left hand and the left foot. What is going to be the measurement that we're going to see here? Again, the projection, that is, I'm drawing a perpendicular line towards this side of the triangle. The projection of the same vector onto the straight line that connects these two electrodes. So basically what you have to do in your mind is dispense with the anatomy of the body for a minute and consider the body to be an equilateral triangle. Okay? Αυτό που κάτω τι. Are we okay? Okay? So, yes, is there a question?
No, that's okay.
Good. We can do the same thing for the third side also, right? So, now if you stay back for a minute and you contemplate this picture, you'll realize something which is very important. And this is what made the Eindhoven triangle very, very useful. That we can really, if we know the geometry of things, if we think in terms of an equilateral triangle, we can always take whatever we measure here and reconstruct for every 2 pairs of electrodes, that is for every voltmeter that we use, for every 2 voltmeters, we can reconstruct the actual axis. We can reconstruct the actual vector inside the body. Okay? Are we clear?
George,
Yes.
can you repeat it once more?
Yes.
Can you repeat it?
I'm saying, if you dispense for a minute with the anatomy and consider the body to be represented by this triangle, okay? And if you consider the measurements that we make with our voltmeters, the way we place them on the body, if you consider those as representing the vortices of this triangle, the angles, then you can take those projections, which is our actual measurement, how many volts our right hand from our left hand differ, and reconstruct what happens inside the heart. Because we need 2 different measurements to take 2 projections, and out of these projections going inversely to recreate this central vector. Okay? Yeah. Now, why is this important? It is important because as you have the total of the heart, you are going to have on it different vectors at all times representing its activity. Okay? And all these vectors can be represented by one large vector. And this large vector happens to be able to be measured where? In the outside of this big triangle. That is between here and here, we can find how much it is, and between here and here we can find how much it is. And since you can measure this and that, this is the voltage difference for one instance between our right hand and our left hand, then we can know for sure what the activity of the heart is. The total activity, but nevertheless the activity of the heart. Okay? Now you are going, once we understand this, we're going to see some interesting things. I propose we take a few minutes break here because this is a nice place to stop for a minute, take a breath, and continue in a few minutes, let's say in 5 minutes, with where this thing leads us. Okay? Okay. Any questions up to now?
Nope.
No? It's not like last time when I had
No, it's better.
when I had totally lost you.
Yeah, no, it's better. No.
Okay. Anyway. Take 5, okay? Ξέρετε ποια είναι η πλάκα. Η πλάκα είναι ότι όταν αυτό είναι το κακό με τα βίντεο.
Because I went to
Ξαφεύγει κάτι.
I couldn't do it.
Και ευτυχώς, δηλαδή χθες γράφοντας, άλλο ήθελα να πω και άλλο έγραψα. Και τώρα μιλώντας το έπιασα. Προσπάθησα να το διορθώσω, αλλά όταν θα βγάλω το τελικό θα πρέπει να αλλάξω και το slide. Η κλειστή επιφάνεια δεν είναι το κλειστό αυτό. Η κλειστή επιφάνεια για να έχεις, στα μαθηματικά, για να έχεις, όταν κάνεις integrate πάνω σε μια κλειστή επιφάνεια, μάλλον όχι σε μια κλειστή, όταν σε μια περιορισμένη επιφάνεια, δεν αρκεί, δεν θα έχεις αναγκαστικά έργο, δεν είναι το ίδιο όσο να πας γύρω-γύρω. Όχι, για το κοινό εντάξει ήταν, αυτό το κοινό ήταν εντάξει. Στο κοινό με την Gauss, το Flax. Το Flax δεν το πέρασα καλά, αλλά δεν πειράζει, δεν τους χρειάζεται τους Gauss. Στο σταμάτησα, αλλά εδώ έπρεπε να σταματήσω. The water is cool, huh? Hello? Hello there. Γύρισα να το βλέπω. Hi. How is the weather out there?
Very nice.
Very nice.
Yeah, it's about 20 degrees.
Oh, 20 degrees.
Yeah, almost.
That's great. How are you guys doing there? Oops. Κλείσαμε το βίντεο.
Ναι.
Εμείς ή
Αυτοί.
δεν πειράζει, ας τις σχέσεις τους.
Τρόμαξα με το που κάθισα στο βίντεο. Θα περιμένουμε να μας πάρουν.
Τι κάνει η κόριτσα μου? Πώς πάει? Wow. Μάλιστα. Τι κάνει ο ξαδέρφος, έφυγε? Δεν πήρα και. Εντάξει. Ναι, και αυτό περιμένω. Ναι. Αξονική. Μπράβο. Ωραία. Μόλις τελείωσα το πρώτο, μέχρι τώρα πάω πολύ καλά. Από το πανεπιστήμιο, από το κέντρο. Το γραφείο από το σπίτι θα το κάνω αργότερα. Έχω. Ναι. Μπα, το δικό μου ίντερνετ είναι καλύτερο. Στην ιατρική περνάει από πολλούς σταθμούς και καθυστερεί. Αυτά. Έγινε. Τίποτε ησυχία. Έγιψε και τα σπάνω ματράγια. Έλα Στράτου, τι έγινε? Πού είσαι? Δεν θα φτάσεις εδώ ποτέ έτσι. Εγώ τι ώρα θα φύγω? Εγώ αύριο φεύγω, αγόρι μου. Δεν λέω για... Τους είπες για το εισιτήριο για αύριο ή τώρα? Ωραία. Ναι, αλλά από εδώ τι ώρα? Εσύ έχεις να πας στο αυτό μετά. Εγώ τώρα είμαι σε διάλειμμα, γι' αυτό σε πήρα. Μ' ακούς? Ναι. Ναι, Γιώργος Αναγιαννάκης, καλημέρα. Ελένη, εσύ? Πέρι, τι κάνεις? Η Ελένη νομίζω είχε κρατήσει κάτι εισιτήρια για αύριο για μένα. Ναι. Καλημέρα. Και εγώ. Όλα πήγαν καλά, ναι. Λοιπόν, κοίταξε, για αύριο έχεις κρατημένη μια θέση για Αθήνα. Λοιπόν, τι ώρα έχει? Θέλω να φτάσω εκεί. Τρεις δεν βολεύει, αλλά τον 11 δεν βολεύει. Ναι. 2 παρά 20 φτάνει. Και αυτό θα με βόλευε, αλλά καλύτερα να πάρω την Αιτζία, να μην έχω λίγο τράτο. 2 παρά 20, 1,5 δηλαδή φτάνει, 1,5 και 2, 4. Ναι, τον 11. Και γύρισε με το βράδυ, τι ώρα έχει για πίσω? Το τελευταίο. Μην κλείσει.
Δεν κλείνω.
11. Με αυτό κλείσε μου.
Σας έχω...
Έγινε. Θα έρθει να το πάρει, ναι. Θα έρθει ο Στράτος. Σε ευχαριστώ. Γεια.
Σας στέλνω την εικόνα.
Hello? Hi. How's everything?
Good.
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 Okay. Now, should I continue? All right. Γύρισε. Okay. We are back to the drawing board. Just to just put together what we just said. The heart activity at any instant is represented by a vector. This vector is measured with 3 different pairs of electrodes, that is with 3 different voltmeters, correct? And because of that, out of the measurements, because of the fact that we use this Eindhoven principle of using the triangle, we can always reconstitute the activity of the heart. Okay? Now, let's see what this means. Let's see what this means. Let's say T0, that is the first minute. The activity in the first voltmeter, that is the one that we represent with Latin letter 1, Latin numeral 1, okay, is a vector going from right to left, or rather from left to right, and let's say that it has a length of 1, okay? Another instant, a few milliseconds later, we can try our measurement again. This vector that we saw in the beginning is going to be changed in position, correct? Yes or no?
Yes.
Why?
Yes.
Why is it going to be changed? Because the different cells are going to have different activity. The activity doesn't stay frozen in time, correct? So at another instant, different cells will be active, different vectors, so the total is going to be different. So this is going to have different projections, and let's say that the projection in the pair that we are looking at the electrode Latin numeral 1, now at T1 is a little bit longer, and in the positive direction. And then in the third instance, T2, let's say that this goes back to 0. Remember this question that you asked me in the beginning? If between two instances where the vector in one side looks at the left and the other side, the other instant looks at the right, if there is a 0 point, you recall this that you asked me earlier?
Yeah.
Okay. So this time, so you don't ask again, I put a time when the vector is going to be 0. By the way, coming back to this triangle, can you think of when the vector is going to look at is going to be read 0 in our voltmeter here? When is this vector going to reach 0?
When it's found 3 will reach the first.
In the first.
Reach 0.
It's going to reach 0.
The
Excuse me?
third axis. The number 3, row 3.
No, number 1. This is when is the projection of this vector here going to look 0? That is just a point here.
0 and 1.
And 1.
When it's straight down.
Either straight down or straight up. When it is perpendicular. Correct?
Yeah.
Good.
Correct.
So either this way or that way, it's going to reach 0. Here. Definitely not in the other 2 electrodes, right? It's going to be much bigger here. All right. Now that we understand that, let's say at another instant, we have a vector looking the other direction, and so on and so forth. Okay? We can then take all these vectors, one at a time, and draw them side by side. We can take, can I erase those vectors here? No.
Yeah.
Well, let me keep them up for a little while. Γύρισε το παρακάτω.
Ναι.
Okay. If this is the time 0, 1, 2, 3, 4, and so on, we can then take the first vector and say, if it looks to the right, it is positive, and if it looks to the left, it's negative. Okay? And then we can put the vector like this, that we measured here. And then number 2 is going to be like this. And then number 3 is going to be here. And then number 4 is going to look down. Correct? We agree up to here? That we can take all these vectors and stash them one side by side with the others? Well, guess what? If we connect these things together, we are going to come up with a curve, which is going to show us in time how this measurement changes.
What does it show? The ECG.
What?
Is that the ECG?
Ah, that's right. This is the ECG derived from the first electrode, which is the first voltmeter, which is the set of electrodes that connect the left hand with the right hand. Okay? So how that looks? It's not that simple as I had it before, but it looks exactly like this. It has a small upward deflection first. This is the 0 line. It makes a small upward deflection first. Then it comes back to the 0 line for a while. Then it makes a small downward deflection next. Then a very large upward deflection comes down, a negative deflection goes back to the 0 line, and then makes another positive deflection again. This is the characteristic sequence of activity that represents the movement of this central vector inside the Einthoven triangle, inside our body that is, okay? And each part of it has to do with certain parts of our heart being activated. So, we call this as the PQRST complex. Okay? And this is the ECG. Okay? Now, do we understand exactly how the ECG arises?
Yeah.
Good. I'm really happy. Now, would you expect the ECG of all people to be the same? Yes or no?
No.
No. Okay. The answer is correct. The answer is no. But you know, all the ECGs fall more or less in this general pattern. Why? Because all of the people, they may have small hearts, big hearts, sick hearts or healthy hearts, and other things, but the sequence of events that follow inside the heart, that make the heart beat, they always follow the same sequence we talked before. So, what is the P wave standing for? The P wave is the excitation of the atria. Right? Now,
Right.
when would you expect the excitation of the SA node to happen? In the beginning, the middle, or the end of this?
beginning.
In the beginning.
At the beginning, correct. Now, when would you expect all the atria to be excited?
At the peak.
Hmm?
At the peak of speed.
At the peak. Okay. When would you expect the SA node to be active?
AV. The SA or
The,
AV?
no, the AV node. Excuse me, the SA we said. The AV. Well,
But Q.
somewhere about here, huh?
Q.
Now, let me try to find a nice picture where they have all these things closely together so we can look at them in one place. Πρέπει να πάω στο άλλο.
Να δείξω αυτό.
Να δείξουμε το άλλο που είχαμε χθες.
Το παλιό, το PowerPoint.
One second, let me switch to PowerPoint presentations. Όχι, μην το κλείσεις αν μπορείς.
Ναι.
Αν μπορείς, αν δεν μπορείς, κλείσει το.
Ποιο θέλετε.
Ποιο είναι αυτό? Ναι, το αυτό. Προς το τέλος θα πάω όμως. Μην κάνω κανένα λάθος, μόνο να πάω.
Πρέπει να έχουμε αυτό. Θέλετε στο τέλος.
Ναι. Αν δεν γίνεται, θα πάω μόνο το χέρι. Κι άλλο. Εδώ. Πίσω, πιο κάτω. Άλλο δεν έχει. Εδώ, άστο. Όχι, αυτό είναι το παλιό. Αυτό.
Το παλιό. Πρέπει να κλείσουμε.
Okay, just give me 1 second to switch PowerPoints because I cannot have two PowerPoint screens at the same time.
Να κλείνω όλα και ανοίγω
Ναι.
αυτό.
Τα άρχισες όλα. Are we okay there? I see somebody's taking a quick run out, dash out. Takashi's tired of listening to me.
Takashi is always on the move. He has like very excited heart muscles, always excited.
Yeah, well, εντάξει. Εκεί, να το δίνει.
Made in Japan, of course. Sony PC.
Για φώναξε το αυτό, δεν έχω.
They make these makers, seriously. I'm not joking. Ask your...
By the way, while I'm waiting for my colleagues here to set up this PowerPoint, are there any questions that we have up to now?
Yeah, it's a lot clearer.
Is it a lot clearer? Maybe you read a little bit the book before?
Some, but
Yeah.
your explanation is best.
Well, you know, this is the beauty of doing things in together, because you know I can sit here and read you a book, but this doesn't mean anything. I mean, I went back the other time saying why you didn't understand, and obviously you come from different backgrounds, and some of you don't have as much of a physics background as I anticipated, to be honest with you. And I'm beginning to come to page now. Okay, just give me a second to get back to the other. Okay. All right. Now, can you see my slides now? Can you see the QRS slide there?
Vaguely.
Excuse me?
Vaguely.
Vaguely. You had it though from last time, so you shouldn't have any problem there.
Okay, we don't see any letters or words. We just see the general shape of the ECT.
You see the general shape. Okay, let me translate a few things for you up in the diagram that I have already put here. Now, this is the atrial depolarization. Okay? We said the moment the atria get excited, and then the time that it takes for the excitation to travel all to the AV node. Okay? Now, this time delay from the P to the R, this time delay is the time that it takes for the AV node to pass the signal onto the bundle of His. You recall that?
From the middle of P to the middle of Q.
To R. It's not Q. This is Q R to the point R. Okay. In other words, the real excitation, the real thing happens right here. This is the time that this is the delay the AV node really imposes. Okay. Now, the QRS complex, which is this part from here to here, including this, so I should really put everything in a box. This QRS complex represents the excitation of the whole muscle of the ventricles.
That's from Q to X? Or
It starts right at where the deflection of Q starts, and it ends where farther down. This is the time it takes to excite it ends up at S. This is the time it takes for the excitation to go throughout the myocardium. Watch out how I said it, okay? This is the time it takes for the excitation to spread throughout the myocardium, okay? But the time that the heart really contracts continuously, okay, is when? Is from here actually all the way to here. All this time the heart is in contraction. And in fact, this part here, the ST segment, is the time when all the myocardium of the ventricles is contracting simultaneously. Over here is the spread of the excitation and partial excitation. We are going to say what parts are excited at which point. But the ST segment is the point where all the heart is excited. Now, why is this zero? If every part of the cell is excited, every cell rather in the heart is excited. It is zero because exactly all the dipoles of the ventricles are active as much as they can possibly be, and because they look in all directions, their average comes to about zero. Remember that these things add up. Some of them look right, some of them look left, some of them look up, some of them look down. But the end result is that because everything is totally excited, the weighted, their total tends to be zero. Because vectors cancel each other. Is that understood? No?
Yes.
Yes.
So between S and T, that's when the ventricles are contracted.
That's right. Because now, why the ventricles only? Because the ventricles are 90%, maybe more, of the total muscle. So what they do at that time literally determines everything for the EKG. So this is the time when everything is contracting. Okay? And then we have the T wave. And the T wave represents the repolarization of the heart. That is the heart relaxing. This is the time when the excitation stops, and one by one the cells stop being active, and the heart returns to its original size, and it fills. Okay? Now, there is an interval between T and P. In other words, I'm going to draw this a little bit more condensed. Okay? Can you see it down below? This is a P, Q, R, S, T. And then again P. Now this distance is the time when the ventricles are filling. Why is it 0? Because now the whole surface of the heart is relaxed, and this is back to isoelectric point because there is very little activity, therefore very few vectors to add up that are non-zero.
Can you repeat that?
Yes, I'm saying the time between T and P and the next P, right? The time here is the time when the heart cells are relaxing. There is no activity. Therefore, there are no small vectors representing those cells. Therefore, there is no additional, the small vectors all add up to, small or zero vectors add up to 0. So, the time the heart relaxes is also isoelectric. Okay?
So the question is why P is not negative? Sorry, T is not negative.
Okay.
If it's repolarization.
It is the repolarization. Why it's not negative, we're going to see it in 1 second. There is no problem. If you have the patience for 1 minute, we can see all these things in a little bit different perspective, okay?
Okay.
Do you see this diagram? Can you see it? Can you see this diagram that I have on the board, on your screen? Not very well. Okay. You already have this diagram from before, so I'll try to go through what you had up here. Well, then maybe, just maybe, I'll draw it for you. Okay, we're going to make a series of diagrams of the heart, and we're going to write on them which part is excited at any instant. Okay? You have to bear with me for a minute, but since we are going to go through this, we might as well take everything down. Okay? Let me start. I'm going to make a very schematic diagram of the heart. All right. I'm going to draw the heart like this. And I'm going to make 4 diagrams like this, or actually 8 diagrams like this. Can you see these things now? The way I'm drawing them? Okay, now we have 8 instances that we have drawn of the heart. We're going to go one by one. Εδώ πάνω, ζουμαρίσε το έξω, να δίνω όλο μαζί. Όλο. Ναι, όχι πολύ, εκεί φέρ το πίσω. Okay, can you see those diagrams? They are just copies one of the other. Okay, now, let's start in the beginning. What we have here? These are the atria, these are the ventricles, okay? And we have the place where the valves are. Now, instant number 1. I'm going to use red color here.
Can you just zoom in?
Yes, we are going to zoom in. Τώρα zoomάρεις το πρώτο. Okay? Now, this is the first part. What would you expect it to be in the QRS? I'm going to draw small QRS behind every diagram here. Okay. Where do you think we are on this diagram in the first instance? Okay, this is the time when what happens? The SA node gets excited, and the excitation starts streaming down to the AV node through 3 pathways. Remember we said this thing? And one of these pathways goes to the other side, to the other atrium, right? So this is the part of the heart that is excited, and this is the part of the QRS that you are in. Can you see the place where I put the red?
Yes.
Okay? You are down here, this one. Okay. So we repeat this situation now for the next one. So now, this time, we are going to have the excitation spread all the way on the atria. Is this clear? So what is going to happen next? Here, what would you expect? We would expect to see this part. Being active. Okay? So this activity represents this part over here. Now, after we do this, after this thing starts, what happens next? What is the next thing that comes in sequence? Who is going to tell me?
The whole circle.
Excuse me? What's going to happen now? This is like the one before, but something more must be added here. What? Remember that we're going to go into the bundle of his, or not? Now, the moment we enter the bundle of his,
There's a delay.
the delay, yes, there is a delay. The delay is here, right? The moment we get into the bundle of his, we are at this point of the ECG. And if you recall, the next thing that will happen is that this thing will excite for the first time the septum between the two ventricles. This is the first part that's going to be excited in the heart. So, by that time, this thing here has finished. You know, there is only little excitation remaining here, but now this part is very, very excited. And guess what will happen to the QRS? This is the part of the QRS that is determined at this point, at this instant. Maybe a little bit more from here also, but this is about it.